Okay, we'll go ahead and get started. It's always a pleasure to open up a prayer, so let me do that, and then we'll give you a sense of what we're going to be covering. So, dear Heavenly Father, thank you for the privilege to be working with each of these students, Lord, to help them understand what it's like to be a systems engineer. And maybe this is helpful for them to be thinking about if that's what they would like to do in terms of their future. Regardless of that, I pray that everything that we will be sharing is going to help them get the job of their choice in their future. Pray that you would also help them in their spiritual formation, Lord, that as they're getting a chance to be studying scripture, as they're getting a chance to be exposed to the theological concepts we derive from that, give them interesting and creative ways for faith integration and help them to be able to take all these things that they've treasured in their heart to apply them in their future. In Jesus' precious name we pray. Amen. Okay, well, for starting with today, we're going into the next major section in our main textbook, and this is where we get into engineering development. So I'm going to be talking about what's called advanced development. And I'm also going to leave a little bit of time for our project work. Since I didn't get a chance to go over it before last week, I'll talk a little bit about the activity diagrams, but very quickly go to the sequence diagrams. Is what we're going to be working on Thursday. So keep in mind, I always like to think of our Thursday as a lab. So have an environment where visual paradigms is working and make it a productive time that you're actually doing it real time when I'm doing it, as I'm giving you a heads up on how to do this. I would welcome you to be doing that. So that's just a little bit of a heads up there. So now this is the first time we got away from this concept development, and there's say the percentage of engineering that's going on, system engineering is a larger portion. In the engineering development, maybe it's about balanced. But now you're starting to do this handoff. And so if you wanted to think of like a relay race, is like you're getting ready to pass the baton per se, and there's going to be subject matter experts that are very focused, that are starting to come into play here. Even like what Kyle was mentioning with his situation that he experienced with some of the lithium ion batteries that they're leveraging. I'll come back to that in a minute. So let me just give a little bit of perspective of what goes on in this area, in this part of the development process. And so the goal, you're trying to be looking at how to reduce uncertainties. So you have a general idea functionally what you want to be doing. Now we're going to actually turn this into something real. And so the objectives of the advanced development phase are to resolve the majority of the uncertainties that is a risk through analysis and development and validate the system design approach as a basis for full-scale engineering. The output of advanced development are a system design. And so now instead of a level A, sometimes you'll have an level A, level B, and level C. And so the level A would be all the system level requirements. Now we're getting into the level B, the subsystem, and reaching down a little bit further. So all those specifications in a validated development model. So you're getting ever increasing understanding of what exactly you've got. So advanced development is especially critical for systems containing intensive advanced development of unproven concepts that may involve several years of development effort. So I'm going to go back to the James Webb. I'll have one slide that will talk about some of the areas that they focused on, but for each of your projects, whether it's a nuclear power plant, a missile silo, a CubeSat, a electronic vehicle, all those things are things that fall into this area where you're having to deal with this development of, or if there's unproven concepts that you're trying to flesh out. Maybe it's a next level of autonomous driving. You're trying to have better performance in missile silos or nuclear power plants, whatever, or you're trying to do something new and innovative with a CubeSat. Activities encompassed by advanced development are requirements analysis. The requirements are always something that a system engineer is having to be aware of. So what you want to be relating the functional requirements to needs. Okay, now we're getting into things that are more detailed and it has to go back to the needs. And so remember the use cases, and we mentioned user stories. That can be the source of requirements. You want to make sure there's a clear mapping. There's a functional analysis and design that you want to be identifying the performance issues. So what are the critical things that have to be working to make this all happen? And I'll use a James Webb Space Telescope as an example to help you get a picture of that. There's prototype development. Some things are so critical and so difficult that you have to be actually build stuff. Okay, using Kyle's example of having some glowing lithium ion batteries that you don't want, maybe you want to have a couple different types of batteries, and you have to be thinking if you're going to put them in space, that's going to be a higher level of radiation. And so there's other potential things that might be an issue. So you want to be, that gets into building and testing prototypes of critical components. And so you have to determine, system engineer, what are the critical components that need to have prototyping done? And then finally get to the test and evaluation, where you do the validating maturity of the critical components. So now that you're doing some testing and evaluation, is it going in the right direction, or do you have yet another option that you need to do in parallel? That could be an example of something that would come out through that process. Okay, so we've had this kind of a rounded square diagram here. Now we're going to be focusing on advanced development. So what, the inputs is now we've done all the concept development from the previous phase. That is then going to flow in. We have functional specifications. We have defined system concepts. All of this starts to flow in here, and then we get into the meat of what's going on here. So we have to be thinking about risk management, subsystem definition, and component specification. So we're getting into increasing detail, and the things that are going to flow out from this are the system design specifications. And rather than functional, now we get into design level and validated development model. And so we have like this digital twin of what we're producing. And so we want to be ever increasing the fidelity of that model. And then we get into the engineering design, which are the next steps that we're going to be doing in this major phase that we're at. We're slowly progressing through this matrix here. So in the concept development, we did the needs analysis, the concept exploration, the concept definition. Now we do the advanced development, and we go down one level more. Now we're not only at the subsystem, the component, but even reaching down into the subcomponents level. Depending on how complicated the system is, you may have multiple layers, and then eventually getting down to the part level, which we'll be getting into in a few chapters. So that's a little bit of a perspective. And then I put in this chart from the James Webb Space Telescope, did an internet search. And this is what they were saying were that the things that were critical that they had to do some advanced development on. And so in order to carry out the mission, several innovative and powerful new technologies ranging from optics to detectors to thermal control system had to be developed. So guess what? It's going to be in a difficult environment. Once it's orbited, you're never going to see it again, but hopefully you're going to be getting the results coming back. And so the James Webb Telescope is having a unique and profound role in transforming our understanding of astrophysics and the origin of galaxies, stars, and planetary systems. And so this reflects back to what's the vision and the goals of the mission are. But in order to carry out its mission, several innovative and powerful new technology had to be developed. There's actually, if you go to the link here that I have, it's the new technology associated with the James Webb Space Telescope. They have Webb spin-offs. And so they develop these technologies, and then they make it available for others to license those technologies. But here is a listing made a little bit easier to read in case it's a little bit small there. Micro shutters. And so guess what? If you're pointing at a really a luminous thing, it's like maybe you've played with a telescope or binoculars, and guess what? You're not supposed to be pointing at the sun when you're looking into a telescope or binoculars, because you're focusing a lot of light into that. And if you think for a camera system, it's the same thing. You don't want to saturate that camera. It's not going to be able to, if you're to have like a really bright source and a really dim source, and you're trying to get that bright source, that's something that you want to prevent. So micro shutters are the kind of technology that you can open and close depending on what you're trying to be able to look at. There's the backplane, all of the infrastructure to keep that all of those segmented mirrors aligned to one another and stable and lightweight. That was something they had to do. Then they get into the cryogenic mirrors. These are lightweight. They have like a honeycomb structure to keep it stable. And then you have the surface tolerance has to be a certain level and a certain type of material. You can see that it tends to have sort of a goldish type of look to it. And this is geared for infrared, not in the electro-optical, the main way that the Hubble Space Telescope was designed to focus on. Then they get into the wavefront sensing and control. And so now you're trying to manipulate things at a very fine level. And so all of those controls that are going to keep things, all of these different mirrors aligned, and keep that alignment down to like the nanometer level or something like that. There's the infrared detectors. Those are things that needed to be dealt with. And this is getting into a little bit of the optical regime, but one of the things that happens in the infrared regime that's different than the electro-optical is that you have black body radiation, and then you're trying to see, you don't want to be imaging how hot your sources are. So you're trying to separate, keep yourself very cool, and then be looking at other things and get that heat energy and whatever it is at those things. And so that's where we're getting into some of the details of infrared detectors. There's also the cryocoolers, and that's because of that, you're trying to keep all of your electronics very cold. And so you're not reducing the sensitivity of what you're trying to see remotely. There is the sun shield coating. They had to do all these fancy multi-layers of sun shields, and then what are they going to put on that coating? And then they also have to be having this data acquisition and integrated circuits that are able to operate very cool in this cryogenic environment. So that just gives you an idea. This is getting a little bit to the end of the scope of what we're going to be able to do with the fidelity of our models in this course, but we're still going to be tracing the whole system engineering life cycle from beginning to end. And now this is the things we're doing all that work in the beginning. It's going to help as we go forward. We also have this chart, and so this gets into the advanced development phase, looking at the various elements. And so all of the concept definition phase elements are what feeds into this. We have to be doing requirements analysis, but now it's at a more focused layer. We chatted about that a little bit. There's the functional analysis and design, and so we want to identify functional performance issues. And so that might lead you to one technology or another. And so here we're seeing some of the things that were identified for the James Webb. You want to be translating that for each one of your projects that you're doing. And then determining, well, what would be the prototyping that you would need? Like Kyle is working on battery technology. And so they found some winners, they found some losers. And so those are the things you do in your engineering development. You document all of that because that's important, because you wanted to understand why you didn't choose this versus that. And so, Abby, I know you're having to deal with battery technology as well. You're not going to be going to space, but it's still, that would be something that you would want to be thinking about. Is Elon Musk with his new battery technology, is that the best one? The Japanese are developing different types of technologies that are out there. And so you could be thinking about that. That might be one of those threads that you'll go a little bit deeper on in your design. You can consider what that would be. And then we get into the development and testing. And so even if you had like a really wonderful capability, but you don't have the means to test it very well, and so you can't have a clean way of validating that and getting buy-in from your customer, you either going to have to come up with that testing technology, or maybe you're going to have to go with something else. And so those are some of the things that you don't want to have your testing limit you, but you need to be aware of that. So what is requirements analysis? That's something we have to do. So we have to, it's the analysis of system functional specifications. And this is where it is required to relate the requirements to their origin and operational relevance. So remember the stick man and ovals we had for the use case diagrams, purposely they're meant to be simple, but that doesn't mean you can't have a very complicated conversation around that. And so this is what we're doing. We're trying to think about how it's going to be functioning operationally. And what are the things that are readily met? Maybe these are some of the critical items for technology that are driving you. There's differences from those of the predecessor systems are also noted, going from the Hubble to the James Webb Space Telescope. What was difficult for Hubble that maybe you're trying to do differently? You have to work out the system functional specifications. These have to be codified into documents. There's a requirement derivation. You go from a high level requirement and then you break it down. Remember, we had this chart where now we're getting into the subcomponent and the part level. And each one of these different parts, subcomponent, components, subsystems, all of those are going to have its breakdown. What is it required to do? And eventually you're going to have to fold that up. That gets into another system engineering function. What specifically is a relationship to operational requirements? Do we just bolt them together and test it? Or do we have to do some analysis and modeling? And then we have to put the modeling and test stuff together. There's a relationship to the predecessor system. If we're trying to get like twice the performance of a previous system, twice the distance for going between charges, whatever it is, whatever analogy. And then we have the identification of component requiring developments. This is the assessment of component maturity, risk analysis, development planning, and risk reduction budget. So whatever you want to be thinking about, maybe it's working on the mirror, going back to this James Webb Space Telescope, maybe it's a cryogenics, maybe it's a microelectronics. All these could be things that you would have to be thinking about. Well, this is something that's in the textbook, and it gives you, say, 4 different scenarios that you might have. And so we have a new function, a new implementation, a new production method, and an extended function. It gives you a relative relationship of the higher the bar is, the more that you're leveraging. So say for a new function, the function is, maybe you still have to capture what that new function is. I mean, if all of a sudden we do autonomous driving, and guess what? You don't need to be a driver. Maybe that's going to open up for more individuals that have handicaps to be having ready access to wherever they want to go. But so we're seeing that there's a maturing area, what's going on for autonomous operation of vehicles. Then we have the physical maturity. And so maybe it's a new function, but you're able to leverage a lot of stuff that's been done previously. So maybe that's in the middle. And then production, well, we've done this before, but now we're trying to do a new function. And so there's saying we could be leveraging a lot of new stuff there. New implementation, so the function is defined, the physical implementation is new, but the production is well established. A new production method, the function and physical are done, but now we're having a new production approach. And so that would be the thing that needs has more risk associated with it. And finally, in an extended function, so all the baseline is there. We're just trying to go from, say, 1x to 2x, trying to squeeze out a little bit more with what you have with your design. Then we have the functional analysis and design. Components that may require further development include those that implement a new function or a new implementation of an existing function, use a new production method from an existing type of component. So this relates to the last chart I showed you. When extending the function of a proven component, and finally, it involves complex functions, interfaces, and interactions. So there's just lots. A system engineer has to be thinking of the big picture, and then occasionally, when they find a problem, they have to go start down and go deep into that one area. They may not be the person that's the primary subject matter expert, but they have all of their phone numbers and they can be fleshing out that this is a concern. We have to work through it to make sure that it's all going to be working. Okay, there's also the critical characteristics of system elements. And in the textbook, there's a variety of different things that they go over here. I'm not going to go through this table in detail, but this is just selected critical characteristics of system functional elements. And here are some of the other things in this chapter that they talk about: extended functional performance, highly complex components, how you're going to be dealing with those. Say there's specialized software, dynamic system elements. What about ill-defined system environments? Okay, it just needs to work in this environment. Well, what does that mean? How hot it is? What is the humidity? Is it, terrestrial? Is it in space? What other, is there a lot of interference that are going on? All those types of things, you would want to be fleshing that out. Functional design, here we get into the functional and physical interfaces, the software interfaces. And so all of those are going to impact what the design is actually going to be, and how and when you're going to be using simulation. That can be a real godsend in a lot of different ways. Well, then we have prototyping. So before they did all of the segmented mirrors for the James Webb Space Telescope, they had to have one successfully work and figure out all the technologies. That could have been an example of a prototype. So maybe they had multiple vendors that they were on contract to be fleshing that out. So prototyping may be used for a variety of reasons. Some may be to get reduce risk to the program, to explore technology limits, or to inform the customer on cost and technology maturity. Program risk requiring development may result from a number of conditions. So say unusually high performance requirements. So you're really trying to go to the edge of what this technology will allow you. So maybe you have to figure out what that edge is, okay? Like computers, just an example off the top of my head, sometimes folks like to overclock their computer. And if you do that too far, it's going to destroy your computer. It's not really a good thing to do unless you really know what you're doing with your computer architecture. You can have new materials and processes. And so that is something where you would have prototyping. Well, can you actually use this material? Maybe it's a new type of battery. Maybe it's a new type of microelectronics. I'll come to this in a second. Like there's silicon, there's gallium arsenide, and then there's gallium nitride, which is a fairly new one that's good for high power conditions. You can have extreme environmental conditions. And so maybe they're saying, well, I now want this to operate in even a more hostile environment. And so that needs to be dealt with, and prototyping could be important. In space, with a higher radiation environment, a lot of times you have to have rad-hard parts, radiation-hardened parts. But you may luck out, you may have good fortune that based on some of the technology, it may serendipitously give you some performance that might actually help out. And so that's something that may happen. There can be complex component interfaces, and there can be some new software elements. And so that's been a huge thing. A lot of things can now be implemented in software. And so that maybe then the trade-off between hardware and software may change a little bit. So there's that. So here's some examples of special materials using titanium, tungsten, other things like that. Glues, I mentioned gallium arsenide, and also one that's sort of emerging, gallium nitride, that is really good for high power applications, and also having some other benefits. And so here we get into these different types of semiconductors. Well, what about glass fibers? That's something, various types of composite material, ceramic components, plastics. These are all within the realm of possibility that may start to come about. So just going back to this James Webb Space Telescope, a lot of this was lightweighting material. So you have a honeycomb back structure for the mirrors. You have the all of the backplane supporting the mirrors that you have here. You can see some of that is just barely shows up in this silhouetted picture. Those could be some things that you are trying to work out. So think about that for your particular application, what you're doing. What do you think some of the core technologies are that you would have to be considering? And then we have to be thinking about the development testing. The further in the development life cycle you go, the more you have to be thinking about the testing and validation. Validation testing to confirm resolution of risk requires the development of a formal test plan, and that's the test evaluation master plan, or TEMP. That's something that's there. Furthermore, test equipment must be developed, validated, validation tests must be conducted, and test results analyzed and evaluated. Some of the things I've worked on that you had to actually design the test equipment. And so then you have to make sure that it's going to stress your hardware, your production hardware to a point that you can validate it actually is going to perform. The results of this testing leads to the correction of design deficiencies. However, special test equipment and facilities often represent a major investment. Therefore, early experimental exploration of interface design is essential. There's also a model of systems and components. We're doing a lot of model-based system engineering with what we're trying to do with our project work. So these are used extensively in system development. Simulations are increasingly important in all stages of development, are essential in the analysis of dynamic systems and software that require development and a staff of analysts and operators. Then we also have development facilities, our installations, simulating environmental conditions. This is definitely seen for satellites. You have to mimic what that space environment is going to be like. And it can actually be, some of these facilities are quite expensive, and there are specialized places where you can go and get those tests done. And so they are used for development, test, and component evaluation. They represent a major investment and require a permanent operating staff. So this is just give you some of the insight into the test and evaluation process. So we bring in whatever type of previous modeling might be done, requirements analysis, so we have a better idea where we're at. We then have the design and build test equipment. Sometimes with the built-in test equipment, sometimes it's called BITE. We then want to be generating the test stimuli, and then we want to be simulate what the system element, what it would do with that information. And so gradually we go from just putting this in and trying to mimic the real life environment of what it's going to be doing. So this is just trying to map that out. There is some feedback. So if there is a source of deviation, we're going to go back and we're going to either have to maybe change our test if that's the issue, or if we've found something with the hardware, we may have to change that. And so those are all the possible things that would happen. And so as a result of this, we have our prototype development, and then we can be identifying any design deficiencies. And then we have to be thinking about, can we live with it underperforming this one subsystem? Can it be made up in another subsystem? And so that is a possibility. Trade-off analysis, that's what that gets into. And then finally, for risk reduction, risk assessment is a basic system engineering tool which is used throughout development, but especially during advanced development. It involves identifying sources of risk, the risk likelihood, and criticality. And so we talked about that in a previous lecture when we went through that risk analysis and mitigation. And so this is something a system engineer has to keep reflecting on as they go forward. Okay, with advanced development, we're doing is we're trying to reduce the uncertainties, make it ever increasingly easy that we can accomplish our goal with our design. We are doing requirements analysis. As we progress, things are getting more and more detailed, more and more all-encompassing. There's a functional analysis and design. as we're starting to go from functional level to specific design details. Prototype development is used as a risk mitigation technique. And so maybe thinking about maybe one or two items, if you were to go forward with your project, what would you want to do in terms of risk development? Risk mitigation, I'm sorry. There's a development testing. Ultimately, you have to test and improve that it works. And we always want to be keeping the risk reduction. And I talked a little bit about that before with some of the things that were going on for risk reduction. Even just before James Webb was launched, they still had a risk mitigation understanding of what they had done and where they were as it was just before it was going to go operational. Okay, well, that's the end for that chapter on advanced development. Any comments or questions on that? Okay, well, let me switch over to talking about things related to our project in more detail next. And I'll do a little bit of a catching up with the activity, and then I'll get into the sequence diagrams. And let's go ahead and just dig into this. And so this is some additional information from Freudenthal. And so I refer to these charts periodically. Tended to do it a little bit more on Thursdays, but since we're right up, we're going to be doing our sequence on Thursday, I wanted to start to go forward with this. And so for activities, the activity specifies transformations of inputs to outputs through a controlled sequence of actions. So with the one or two activity diagrams that you came up with, you've got some familiarity with that. The secondary construct shows responsibility to the activities using activities partitions or swim lanes. And I was encouraging that you think about that. And there are some SysML extensions to activities. So this is SysML specific. There's support for continuous flow modeling. And it also has better alignment of activities with other types of tools like the advanced functional flow block diagrams that we had mentioned previously. So here is an example of control power activity diagram. So you can have a start and an end. We have two swim lanes that we see here, and then we go from one activity or action to another. And eventually it goes out. So you can be annotating like that. You can also have ports. I haven't really talked about ports too much yet. And we also just briefly touched on starting and executing of something. So this is the nomenclature for seeing what that would look like. So this is provide power activity diagram. So this is Freudenthal uses a car analogy here, both in his practical SysML as well as some of the other things with the SysML model for doing something with satellites that I have been showing you in my Cameo Systems modeler. And so this gives you just another example. Now we have a lot more swim lanes, and so you can have that showing. And so there tends to be a flow from the input to the output. That's what we're seeing in general, what takes place with these types of diagrams. And sometimes there's conditions that it goes from one to another. So actions describe how activities execute. And so here it's used to model the steps of an activity. So actions are one step below an activity. So an activity can have actions within it. And so that's what we're getting a little bit of insight in here. And so it accepts inputs and creates outputs. And their call actions represent activities that can be further decomposed into other actions. And so you can do decomposing in an activity diagram with call behavior actions. That's something that's possible with this. So here are some of the syntax. You have a start, an end, and then you have a termination of a particular sequence. And the sample that I showed you had examples of all three of those that were possibilities that can have. You can also have fork and join. This is the way how you can have a breakout or fan out or a combinational circuit going down to a single output. That's something that you can use. You can have decision nodes. And so this is where you can have some control logic that it either goes to one or another based on some type of a criteria that you have established for it to take advantage in that situation. You can have different kinds of arrows. You can have control flow with a dotted arrow. That's something that you can be doing. Really didn't get into some of these details quite yet with the level that we've talked about here. This gets into probably close to what you had with your activity diagram in terms of the level of complexity. And so this is for the intruder system, and you can see two swim lanes here. You have the operator, and then you have the surveillance system, and you can see this engagement between those two things being laid out. And these can actually get fairly complicated. I've been trying to keep them relatively simple for what we're at right now. This is kind of easy. It's just just steps you right through, so you can have a fairly simple activity model. There's no decisions, there's no branching or anything like this. Here we can have a little bit of more complexity, so we go from simple to now we're trying to be giving more information into the flow, the ports. That would be something that we have there. And then we can actually put that into swim lanes. And so you could see that you could start to develop something, and then you wanted to do some further annotation to make it clear to show how things get involved from one unit or subsystem going to another. So I think this is the gate example. And so how much do you actually owe when you're trying to leave the parking lot? And so this just gives you an example of what would be the amount that you would have to pay for you to actually be able to leave. And then when it's done, it's not going to engage with that individual further. So that's just a reminder of some of the things we have in the activity diagram. The next thing that we have now is how do we model message-based behavior with interactions. And so sometimes some of you, maybe you like playing with computers, and there's like something called an ACK, an acknowledgement. You send something and you want to get an acknowledgement, so depending on how complicated the exchange is for exchange information, sometimes it's just broadcast. Sometimes it's a broadcast and it wants an acknowledgement. It starts to give you some of that perspective and what it can be doing. So a sequence diagram provides representation of message-based behavior. It represents flow of control, describes interaction between parts. The sequence diagrams provides mechanisms for representing complex scenarios, and there can be reference sequences and well as control logic. So here's a real basic way of thinking about it. So this is with a car, we have a driver in the vehicle. So you start the vehicle and you want to get some type of feedback that the vehicle is on. Guess what? If you have an electric car, that's a little bit harder because you don't have this engine that's all of a sudden it's making noise and the car's jittering a little bit. But there needs to be some positive thing, the display comes on, and so you get an idea. So this is an example of a simple sequence diagram. This next one's going to be complicated, and so almost just wanted to preface before I go to that slide. And so here we have a sequence diagram, but it's also showing a lot of other things going on, and still it has things at a higher level. So we have a PAR. We're going to get that. That's be like the last diagram we're going to talk about, the parametric diagram, where you get into the physics that are having things happen here. And so this is just things that this is a little bit more complicated. So I'm not going to spend a lot of time going over this, but just wanted to at least flash it up to give you a perspective on it. So maybe just starting with something simple here. Well, what are the elements that you're going to be engaging with? I'll pull up visual paradigms just real quickly in a minute, but I'll defer to going over it in more detail on Thursday. So a sequence diagram can be comprised of the following. It can have lifelines. So that's what we hear. These dotted lines are lifelines. And so these are the things that you're going to be trying to annotate the flow of information or sharing of something. It represents a structural element of a system, and it depicts time. And then messages, it can be asynchronous, synchronous, or reply. All of those are possible things that would be what's going on. Here, once again, we see another simple example, a sequence diagram for opening the gate. So you get the processor is telling the gate motor to do something, and so it's a Boolean. It's either open or closed, true or false, and then it responds by opening the gate. And so there's some response that's coming back to the processor and say that that command was successful. That would be what we have there. So sequence diagrams are used to depict the interactions between structured elements of a block. Sequence diagrams are comprised of lifelines. And so those are the dotted lines here, like what we see in that. And messages. And so we see those are the things that you're going to be conveying from one to another. Lifelines represent a structural element and depicts time. And so you can see that we have to do this, the processor passing this desired opening of the gate before you're going to get the gate opening. So there's a temporal sequence starting to be laid out with this. Messages can either be asynchronous, synchronous, or reply, and messages represent a call for an operation. Combined fragments are used to depict complex interactions and include alternate paths, parallel paths, optional paths, or loops. And reference interactions depict reuse of common components. So maybe you need to have an aggregation of a couple things before you could then say, okay, I got everything I need to do what I want. That's what would be possible with combining fragments. Any questions on that? Just trying to give a high points introduction to what that's all about. And then I'll just quickly go to visual paradigms and give you a heads up on what we'll talk about on Thursday. And we can actually create one real time. Like I said before, it's always a great idea to back up your work. And so hopefully you guys have come up with a scenario that's working for you guys. And I can tell you, like recently what I did is I started to use OneDrive to do backups. And so here I thought I was covered, and it actually that wasn't quite the case, that it was actually it was messing up some of the other things that I had done. And so I actually lost some things on my computer. Fortunately, because I had a backup, it was a little bit more precarious, but I was eventually able to do a recovery. And so I'm just trying to say that to give you a sense of these things actually unfortunately do happen. So I'm going to try and make sure if I just pull out a simple one to begin with. And so yeah, this is probably kind of the level of sophistication that might be good to think about. And hopefully what you're starting to see is you can continue to make these things more and more detailed. So I'll just zoom in so it's easier to read. So here we can see a flow, and so an operator. So this would be a CubeSat controller. So this is closer to what Kyle is doing. And so here we can see these different types of folks. So we have the operator, the ground station, the CubeSat bus, and the CubeSat sensor. So this is try and show the CubeSat. TNC is shorthand for telemetry and control flow. So here I do the commanding. Okay, I want to command a satellite. And so these bars here, these are, if I wanted to stay, do a new kind of add to this, it's the same way that you do it, but if you just hover on this, you'll see this little thing that you want to be creating a new line to go from another, and you're going to be creating these bars that are along these lines here that we had. And so so the first one, we have a CubeSat command. Then it goes to the satellite, and so the bus has to verify that command. Once it has authenticated, then it actually attacks the sensor. And what I'm showing here for this TNC flow then acknowledges the collection, and then it passes on the collection from the bus down to the ground, and that collection goes to that that command and control GUI that the operator has. That would be an example of something that we'll be talking about. So they can start out fairly simple. They can get more involved. And you might recall that when I was showing the Freudenthal, that it had these boxes here. So this is something you can be doing. And so here I was just labeling these loops. I think this came from a previous student, Karina Gray. Some of you might have heard her name. And I think this was one of the ones that she created. And that's another one that shows you that same kind of a construct. Just so we'll talk more about this on Thursday, but I just wanted to give you a few heads up. You can begin to try and playing with this, read through Freudenthal and review some of the things that we had today. And I think it'll help you prepare for Thursday. So any comments or questions on that? So hopefully you're starting to see that each diagram type has its own merits. And so sometimes we use one or the other. And so we'll get a chance to now integrate this new perspective with a sequence diagram as we get into the details on Thursday. Okay. All right. I think that's a good breaking point. So thank you.